let's look at an example where we study a random variable L minus defined as the liminf of xn when n goes to infinity in this way. And what does this mean precisely? It means that we define this in this way. So for every omega, we can look at these omegas and we have a sequence of real numbers for any omega when we input it there. And then for that sequence, we look at the liminf of the sequence. So we actually, what we are looking at, we can always also define the liminf by taking the supremum of n, and then we look at the infimum of m bigger than n of xm. Okay, and let's also give this part a name. Remember, infimum is the greatest lower bound, so biggest number that is less than each of these xm. Here we give this a name, we call it L minus m. So it's kind of a lower bound of this sequence. Wait, there's something wrong. This cannot be m, this should be n, of course. Yes, it's L minus n. So this L minus n is the lower bound of the sequence from n onwards. Okay, let's make a picture so that we maybe have a feeling about this. So we look at the sequence. So here, if this is index 1, so we put there something. For index 2, we have something, and maybe 3 there. And then at 3, we may have here a value, and let's see, maybe there. This is not an easy thing to draw, but let me try to do my best. So maybe we assume that from that on, we get something of this sort, that there's alternating things with this type of setting. Let's update the picture a bit. That's where our index is going. Let's clean up a bit here. Okay, so let's look at the sequence of this sort. So that's the first element, the second one, third, and so on. And we look at what is the liminf of this sequence, and we should look at also actually what is this L minus n in this. Assume now that this is a random sequence, so we do a one sampling using a random number generator. So we sample one sequence of this sort, and for different omega we get a different sequence. But anyway, after we sample the omega, we can look at this random sequence, the realization of the sequence, and okay, and just try to understand what is the liminf of the sequence. So now L minus 1, what is that? So L minus 1 is equal to infimum of all m bigger than 1 xm. Yeah. So that's the full infimum, kind of full inf. And in this picture, what is the smallest value? So it's this one here. Yeah. So L1 is actually this value here. And if we calculate L1, so then L minus 1 is there, because that's this value, the full infimum of the sequence. Then we calculate what is L minus 2. If you look, then it's the infimum m at least 2 of xm. And what is this value from the picture? So L minus 2 is then, we omit this first value, and then we look at the in from starting from 2 onwards. So now we start from index 2 and we look at the infimum of this sequence and we see, well, it's the same value here. So in this case, L minus 2 for this sample, it's equal to L minus 1 as well. The same is true for L3 and so on. So actually L2, L3 is there, 4 is there, 5, 6, this 7, that's where we get something interesting going on. So this L minus 1 is here, L minus 2 is the same value, L minus 3, L minus 4, L minus 5, L minus 6. We get these same values and then we are here. Then what is L minus 8 in this sample? So it's the infimum of xm from number 8 onwards, index 8 onwards. So index 8 is here. Now we are not able to allowed to look at this. So then the infimum is this value here. And that's the what we put for L8 and also for L9 and so on. And this way our infimum kind of type of thing works this way, and then it jumps here and it plays there and it jumps after this one. Maybe this is the smallest value. Okay, the picture gets bad, but then it remains constant. Okay, so what I have sketched here, this is the sequence L minus n in the red. I hope this makes sense to you.
Can I ask quickly?
Please go on. Yeah.
So in order for infimum to exist, the set must be non-empty and bounded below. So what guarantees the boundness below in this case?
Nothing. Excellent question. Thanks. What about the existence of the infimum? So, okay, this set is non-empty. When we look at these are non-empty collections, so that's fine. But what if this is not bounded from below? So what's the infimum then? If it's not bounded from below, so actually what I would like to tell you is that we might be looking at the extended real numbers. So we might define this as minus infinity when things are not bounded from below. So now it's a little bit up to your taste. Actually, this is a little bit complicated, and that's why this lecture is not big pleasure to, well, maybe it's a pleasure to give, depending. It's maybe pleasure to speak, but maybe not pleasure to listen because there's a complication with infinities. So if you like, you might like to work not on the real line, but you might like to work on the extended real line, which means that we add this minus infinity and plus infinity to the picture. You might like to work with this. Then the infimums always exist and you don't need to worry about those. If this feels a little bit confusing, so then what I recommend you for this lecture, we assume that xn, assume that these random variables are bigger than 10 to the minus, they are bigger than minus 10 to the 100, and they are less than 10 to the 100. Okay, so if you make this assumption, your practical applications wouldn't hurt. You would assume that this is true with probability 1. So for every sample omega, every random variable is between these two bounds. And then you would think about this game, and these infimums and supremums wouldn't hurt you. They always exist. Depending on how kind of how friendly or familiar you are with infinities, so you might choose one of these options for when you are listening now. Yeah, in some textbooks, actually, this one is often mentioned, and also maybe in the lecture notes this is mentioned, but it's not described in high detail. Actually, yesterday evening I thought about this. Okay, how to speak about this. So I wrote a bit of 3 pages of lecture notes myself about this, and maybe I could share it to you if you're interested in knowing. Okay, like just looking at the details, how to describe the Borel sigma algebra on this space and so on. Okay, but thanks for this question. It's an important question actually. So we might think that this is minus infinite, and you should somehow hopefully trust me that it doesn't cause anything serious. So anything that we couldn't treat with this measure theory. All right, but maybe to go on, what is actually that is the purpose of this example? Actually, the claim is that my claim is that this L minus is this is measurable with respect to the tail sigma algebra. And intuitively, if you think, okay, you are looking at the sequence, you look at the liminf, the kind of largest lower limit that you can look from the sequence. So if you omit finitely many values from the beginning, it doesn't affect the liminf. That's the intuition. That's why the liminf should belong to this tail sigma algebra. And how to kind of understand why this is true? Technically, it's not difficult actually. The most difficult thing is to recall the definition of what this liminf means. So, but with this red ink, I think we have a picture about this. And what's the important thing about the picture? You see from the picture that L1 is less than L minus 2 is less than or equal to L minus 3 and so on. So this red thing forms an increasing random sequence. So it's increasing to something. And that's why it's increasing. So we actually conclude that this L minus n is increasing to L minus, because L minus, if you look, it's the supremum of an increasing sequence. So if something increasing, then the supremum is in the limit that you get. And again, this supremum, if you don't have bounded things, so it exists in the extended real line. And actually, what this proof is going to be is to say that L minus is actually is the tail sigma algebra Borel extended real line measurable. That's actually what we are claiming here, to be precise, in full generality. Okay. Yes. Is this correct? Let's see. Yep. So we have an increasing sequence, and then we could look at this Ln. So if you look at this L minus n, and we know that it's an infimum of m bigger than n of xm. So each of these is measurable with respect to the calligraphic xn, because wait, there's something wrong. No, each of these is measurable in the sigma algebra xn plus 1, etc. And this is what we defined as tail n minus 1. So, and that's true for all m bigger than n. So we have a collection of random variables. Each of these belongs to Tn minus 1. And we have a proposition that the infimum of measurable random measurable functions is again measurable. So that's why this one is this one, this infimum is also Tn-1 measurable. That's the first observation. Maybe I clean this one. So that's true. And then let's see. What do we say about the supremum? Yes. Let's look at L minus is the supremum of this L minus n. That was the definition of the liminf. Now we are looking at an increasing sequence and supremum of this. So it's the same supremum if we omit finitely many initial values. So let's say we take the supremum n bigger than, let's say n strictly bigger than some k. If you look at this, we omit the first k values. This is still the same supremum as here because we are looking at the supremum of increasing sequence. And that's why, and now each of these L minus n, each of these are Tn minus 1 measurable. And because n is bigger than k, so they are also Tk measurable. Because Tn minus 1 was, let's see in the beginning. So we remember that these T sigma algebras were ordered so that this is the smallest. And that's why if we go back here, so Tk is smaller value. So this goes that way. Yeah. So each one of these is actually Tk measurable. And that's why we are taking a supremum of something, each of which is Tk measurable. So that's why the supremum also is Tk measurable. Okay. So we know that we conclude that Tl minus is Tk measurable. And but what is k? K was just some integer, yeah. So actually this is true for any k, any integer k bigger than 1. So that's why L minus is actually, this L minus is also in the intersection measurable. So we can take the intersection of these, and that is the tail sigma algebra. So a little bit complicated thinking because we had to work with sigma algebras and stuff, but the final conclusion is that the liminf is measurable with respect to this tail sigma algebra. And maybe it is not completely easy to listen this explanation here, but I recommend you to now read the lecture notes about the same description. Now that you have seen the picture and heard maybe my bit of my ramblings about this, so it might be more easy to read the lecture note if you want to look at the details of this part. The key thing was that we used to know that the infimum of measurable is measurable. So we use proposition from chapter 3, where it's proved that the infimum of measurable is measurable again. Okay, do you have questions about this derivation? Maybe you like to ask something, but maybe it's intuitive, I don't know. it would be soon good to have a break. We conclude this example by a couple of remarks. Another claim is that L plus, which is the limsup. So limsup and liminf, if you know one, how to handle one, then you know how to handle the other one. They are dual. So the upper limit, the limsup of xn, is also in the tail sigma algebra. So it is measurable with respect to this tail sigma algebra. And the proof is similar, so we skip it. And finally, let's say consequence. Let A be the event that those omegas for which the limit of xn exists. So think about, we have a random number generator which produces us random sequences. Okay, whenever you sample one, you get the random sequence. You sample again, you get the random sequence. For some omega, for some samples, your sequence might converge. For some other samples, it might not converge. And then the question is, what about A? Does my sequence converge or not converge? And I'm claiming that this question, does it converge or not? That's one event in the tail sigma algebra as well. So I'm claiming this. And now we can prove this easily based on actually the previous thinking. So how to prove this is that the event A is actually the event that the set of those omegas for which the liminf omega is equal to limsup omega. Yep. A sequence converges if and only if the limsup is equal to liminf. And then we can look at the complement of A, which is now the complement of this, and the complement of A is the set of omegas for which L minus omega is strictly less than L plus omega. Yep. And what about this? Is this some kind of nicely measurable event or set? Not immediately, but let's say that if L minus is less than L plus, so then there exists a rational number in the middle. So we can write this as the union of all rational numbers. And then we look at the event that L minus omega is less than the rational number, and the L, sorry, this is L minus and this is L plus omega is bigger than the rational number. And if you look at this union, so then this is the union of rational numbers, and we look at the pre-image by L minus 1. So now we should look at the pre-image by of minus infinity, or maybe we include minus infinity actually here now because it could be there up to Q. And then we look at the intersection that L plus must be bigger than Q, so it's the pre-image of L plus for the interval from Q up to infinity on the plus side, and then we look at all of this. Looks complicated, but it is not, trust me. What about this here? This is a Borel set because it's an interval. It's also a Borel set if you include this infinity in the extended Borel sigma algebra. And this is a Borel set here if you look at this one. And so we know that L minus is measurable with respect to the Borel and the T infinity. So then we have a pre-image of a Borel set of a measurable map. So then this guy, the pre-image here, because it's a pre-image of a Borel and we have a measurable map, so then this is in the tail sigma algebra. And so is this. This is also in the tail sigma algebra because we have proved that these are measurable things. We have measurable set, intersection, measurable, so it's measurable. We have a countable union of measurable sets, it's measurable. What do we conclude? We conclude that A complement is also in the tail sigma algebra because we were taking intersections and countable unions of elements of this sigma algebra. And because this is stable under complement, so then that's why A is also in the tail sigma algebra. That's the end of the corollary or the consequence proof. That asking if is there a limit or is there not a limit, we can ask it and that the answer, that event belongs to the tail sigma algebra.